Okay, so in this lesson, we're going to discuss inverse trig ratios. In mathematics, we use inverse operations to undo procedures or extract variables. So the purpose of inverse trig ratios will be to extract the angle so we can solve for the angle. So some examples of where mathematics uses inverses is addition and subtraction are inverses. We use those to undo each other. Multiplication and division are inverses, except division by zero, which is not defined. The inverse to squaring a value is the square root of that value. And in mathematics, the notation for inverse of functions is a function with a negative 1 in the superscript. So we would read this as f inverse of x, and it is the inverse to the function f of x. If we compose a function with its inverse, that means if you put the function inside of the inverse function, you will get out the argument, or x. You can also put the inverse function inside of the f of x function. Again, you will get the same result. You will extract the variable x. You'll talk more about these topics in Algebra 2, but we just want to introduce you to this notation because it is the definition of inverse trig ratios that we're going to apply. So you're going to see notation with negative ones in the superscript. So if y is equal to sine of x degrees, then sine inverse of y is equal to x degrees. So how do we get this? Well, with everything in mathematics, anything we do to one side of an equation, we have to do the same exact thing to the other side. So if I start with sine or y equals sine of x degrees, I can say let's take sine inverse of the left side of the equation and sine inverse of the right side of the equation. And what happens is sine and sine inverse cancel each other out. So we simply get sine inverse of y is equal to the argument, which is x. Basically, we've extracted the angle. And now that we've extracted the angle, we can go on and plug the rest of this into our calculator. So these are the definitions and how they are read. We see that sine with a negative 1 in the superscript and y as the argument is read as sine inverse of y. The same is true for cosine, that is cosine inverse of y, and tangent inverse of y. Here is the textbook definition. We see that if tangent of a is equal to x, then tangent inverse of x is equal to the measure of angle A. We took the angle from the tangent function, and that is what we're solving for. And in this case, x could be the ratio of BC over AC. So we need to find the sides of the rectangle or the triangle that make up the parts for the inverse trig. Let's look at an example so we can better understand this. Which of the angles are being described? If we say that the sine of an angle is 12 over 13, well, we have to remember that sine is equal to opposite over hypotenuse. We know that this is the hypotenuse. That's the easy part. So it means opposite has to be 12. Well, if that's the opposite, we must be talking about angle E. So sine of angle E is equal to 12 over 13. Now, if we want to solve for angle E, we take sine inverse of both sides. And the sine inverse and the sine will cancel, leaving just angle E is equal to sine inverse of 12 over 13. And this is where we get our calculators out. And you'll notice that above sine in blue is sine inverse. So we have to hit the second key, sine. You see on the calculator screen, sine inverse is there. And we'll put 12 divided by 13, close the parentheses, hit enter, and we get 67.4 degrees. So which angle are they talking about in problem 2? Let's clear some of this ink out of the way. Well, tangent is opposite over adjacent. Again, we want the angle that is opposite for 5. Well, opposite of 5 is angle F, and adjacent to angle F is 12, so 5/12 makes sense. We should say that angle F is the angle being described. And now we can go on and say tangent of angle F is equal to 5/12. And instead of writing the inverses on both sides, we always know that the tangent is going to cancel and extract angle F, so we can start to shortcut what we're writing out. And now tangent inverse of 5/12. And we will plug that into our calculator. Second tangent, 5 divided by 12. And we get 22.6 degrees. And if you were to add these two angle measures up, you would get exactly 90 degrees, which makes sense with our triangle. We have a 90-degree angle. The other two angles add up to 90. That gives us 180 degrees. So in this section, we're just going to get some questions where the textbook just tests us that we are actually entering our inverse into the calculator correctly. So the first one we see is done. If we want to solve for angle A, we're going to take tangent inverse of 0.75, and we get an answer of 36.9. So now if we want angle B, because it's with sine, we're going to say sine inverse of 0.87, and we plug that into our calculator. And that is 60.5 degrees. And then for angle C, this will be cosine inverse of 0.15 degrees. Cosine inverse of 0.15, that's not degrees. We're going to get degrees out, 81.4 degrees. So that's just calculator entry with the given information. So whenever you see a problem say solve the right triangle, it means find all of the unknown measures. That means the sides and the angles. So we need to find side C, angle A, and angle B. So we can do this by saying, well, side C, if I wanted to, I can solve for that using either trig or Pythagorean theorem. Because it's a right triangle and I know two of the three sides, I can say C squared is equal to 2 squared plus 3 squared. C squared is equal to 4 plus 9. C squared equals 13. So C is the square root of 13. So we can use Pythagorean theorem to solve it since we did not know any of the acute angles. And now we can solve for the angles. I can say, well, from angle A, 3 is opposite and 2 is adjacent. So tangent of angle A is equal to 3/2. Therefore, angle A is tangent inverse of 3/2. Plug that into our calculator, and we have second tan 3 divided by 2, enter, 56.3 degrees. And because there's a 90-degree angle, we know that angle B will be 90 minus 56.3. 33.7 degrees. So we used a combination of inverse trig, 180 degrees in a triangle, and Pythagorean theorem to solve for the three unknown parts of a triangle. And here we have an application problem, and the application problem will allow us to solve for the angle of inclination for the stairs. It says the horizontal part of a stair is called a tread. We see that's highlighted in blue. And the vertical part is called a riser, highlighted in red. The recommended riser to tread ratio is 7 inches to 11 inches. So the riser is 7, the tread is 11. And if we take this out and draw a triangle, we want to figure, well, which angle does X represent in that triangle? And if we look at parallel lines and transversals, X degrees would go into this part of the triangle using the alternate interior angles theorem. Now we can say 7 is opposite and 11 is adjacent. That means we're using tangent of X degrees is equal to 7 over 11. Tangent inverse of 7 divided by 11 gives us an inclined angle of 32.5 degrees. So that is the angle X for a staircase that has a riser to tread ratio of 7 to 11. Because they said riser before tread, that means 7 inches went to riser, 11 inches went to tread. That's our ratios unit. We have to remember to follow the order that it was given to us in terms of the word to or with the colon between the numbers. And part B says if you want to build stairs that are less steep than the stairs in part A, give an example of a riser to tread ratio that you could use to find the value of X for your stairs. And again, if we want it to be less steep, that means X should be a smaller angle, X less than 32.5 degrees. And you can either increase the length of the tread or decrease the height of the riser to accomplish that. And you can choose some numbers and play around with it and solve for your X and see that that's true. Okay, so that is the end of the presentation. Take notes, do the practice problems, check your answers, bring questions to our next class.